All right. So I guess I'll address this question. Yeah, I don't know. I'll have to double check. Has anybody else been having this problem with the tutorial? Yeah. Okay. So, uh, I think it's tutorial 7. Maybe I uploaded the wrong documents, but I'll double check to see what happened. Do you guys remember what's the topic? Like, have you tried the questions? Okay. Yeah. All right. So maybe what did I do? It's weird. Um, oh. Is it supposed to be linked lists? Is that right? Yeah, okay. So I probably gave you the wrong stuff. I don't know. All right. Well, I'll look into it regardless. The past tutorial, it's the present tutorial, right? It's the one this week. Is that okay? So the one this week. Yeah, please let me know if that happens because I don't know. Whatever. I can make mistakes too. So all right. Yeah. So today is November 12th. We're going to talk about streams and files. I guess in bigger picture wise, so I'll fix the tutorial. Anybody who needs like extra time, just let me know, right? That's pretty, I'm not super rigid on that. I just, it's helpful to set a due date, I think, for everyone. It's just to put it in our rear view mirror. But um, and then assignment 4 is due this weekend as well, and then the midterm next week. So that's the test number 2. So that's sort of the big thing. Um, so what I was thinking of doing is on Thursday, having a review. The reason Thursday rather than next week is because it'll give you more time, but also it will force me to make a practice quiz so that you can get it early. Otherwise, you probably won't get your practice quiz till next Tuesday. So really, it's up to you guys. I'm fine either way. It's the same amount of work. It's just when I do what. So Thursday, you guys want Thursday? Yeah, okay. So this Thursday will be the review. I will have and then you can go back. It's a video. You can go back and watch it if you want. Um, because it's multiple choice, some of the questions are like tricky, right? So I'll try and give you some hints along the way so that you can, so that if you study, you do well. That's the idea. At 5, that might be, I mean, I think I can get it done this weekend, but possibly it may not be released right on Monday, right? It might be Tuesday or Wednesday. But I'm assuming that we'll be focused on the midterm and assignment 5 will be doable in 1 week, right? So that's the idea, is that you would only need really this week to do it in. Other than that, I guess, I don't know, man. I'm feeling, the professors go through the crunch period like a couple weeks before you guys do. So the end of the semester is busy for you. Like this time of year is extremely busy for me, but yeah. So if I make a mistake and like don't put the right tutorial stuff up, please send me an email. But yeah, any questions? Yeah.
What topic will it cover? Is it hitting after bitwise operators or
Bitwise operators?
yeah, everything.
Oh yeah. So everything up till technically everything let me think here. Anything you've seen on an assignment, I've considered fair game. Anything outside of an assignment, I will give you fair warning about. So our assignment had to do with like so far we've done structs, memory management, processes, and sockets and threads. Okay, so that's what we'll focus on. And so during the review, I'll make up. I mean, it's harder to make a practice exam for multiple choice, but I'll do that, and then we'll just go through some of the questions to sort of. Again, I just want you guys to focus on the right things, the stuff that'll get you marks. So, yeah. process is equal to a program. Essentially, yeah, right? It's a running program. Um, but more to the point, like things like, well, one of the questions has to do with a fork, right? So I give you a piece of code that calls fork at some point and it prints out some stuff. And so then what is the expected output sort of thing, right? Stuff like that. Those are easy multiple choice stuff. Stuff like threading. If I give you some code that runs a couple threads, what's the expected output, right? And then so you have to know if I'm using a semaphore, what sort of impact that will have. And if I'm not using a semaphore, what sort of impact that will have. And then other than that, like a lot of, so linked lists also, right? So you guys should have written some linked list code. So I'm going to ask you to, like choose which of these implementations you think is correct for this linked list function. And then, I'll try and trick you because I'm giving you the code. So I think it's fair that it's a little bit tricky. So like keep your eyes on the details. So linked lists and a lot of focus on, which we're going to cover a lot during the review, but like just making a struct, what are the different ways I can make a struct, right? What are the different, like, what does it mean in terms of memory? What does it mean in terms of how I access it? Like, do I use the arrow operator? Do I use the ampersand? Do I use the dereference? Right? So there's going to be a lot of that. So, and that stuff's like difficult on a good day, but so we will be reviewing it so that you guys can hopefully have something to study from that'll help you be successful. All right, other questions? Okay. All right, so we left off last class with threads. Today we're going to start talking about files and streams. We did briefly start talking about it, but not really. So streams and file input output. Again, I mean, it seems like everything in this class falls under the same theme. Like here's some bytes. How do I get these bytes from here to there? And how do I interpret them, right? And that's basically like well, that's everything to do with memory, right? How we interpret bytes from memory. That has everything to do with sockets. That has everything to do with threads. And in this case now files. So now I'm moving bytes from memory to my disk. But basically when we're talking about a stream, we're talking about a sequence of bytes. So we can talk like if I'm typing a bunch of characters, that's a stream of bytes. All the stuff coming through your router, including Netflix or whatever, those are streams of bytes. And when I read and write data to and from a file, that's also a stream of bytes. And a text file, I'm using it very loosely here. Typically it means like moving. So like I am getting some incoming bytes or outgoing bytes, but can also just be a bunch of memory, like static in your file. That can be a stream. And then instead of moving the bytes, I just move the pointer, right? All right, so IO is short for input output. So input, I transfer bytes from a data source, right? So, well, we've all done this. Like I have a play games, or I read from a file, or I stream something from a network or whatever, or I have a program that I read from. And then output, I transfer bytes from my program to somewhere else. Like I can output them to the monitor, I can save them to a disk, I can send them to the printer, or I can send them to another program. So when we set up a program, typically we have some streams that are set up for us, right? So they are called the standard in, the standard out, and the standard error. So standard in, you've used with the keyboard, right? So this is scan F will read from the standard input. Standard out is the display. So print F prints to the standard output. Now you can redirect these things. I'm not familiar how to do it in C, but I don't imagine it's that hard. I can do it. I know how to do it in C++, but standard error is again by default the display. But yeah, technically it's a different stream. So you can do things like you can redirect it to a log file. So if I want to log my errors, and if I'm capturing output in my program, like if I write some code that tests your code, I capture the standard output and possibly the standard error, and I maybe just print the standard output and keep the standard error or something. And we can redirect all these streams to other places. So yeah, all of these streams, especially in C, have basically two main data types, right? And I mean, I think that applies to almost everywhere. But basically, at some point, the people who made Unix, and then that became Linux, and then they developed C on it, and then Linux was rewritten in C. They decided that all config files should be text, right? So they decided that text was a very good data representation tool. First of all, because, well, for a bunch of reasons, which we'll talk about, but, basically we could read it. And it's really not that much worse than this, which is maybe I just take all of my structs or what have you, and I just write them straight to memory, right, as is, right? If my struct is 20 bytes, I just take those 20 bytes and go and put them on disk. And then when I come back later, I read them back as those 20 bytes. And now I have to know what kind of struct to read them into in order to figure out what it is. But yeah. So text, readable, so we can easily read what is stored, right? So a lot of config files in Linux are in text. I think almost. Data can be recovered easily and naturally, right? So maybe there's a mistake. Somehow the file got corrupted. Somebody inserted something that's not supposed to be there. Well, I can kind of fix it, right? I can open it up in a text editor and fix it. Text has a high compression ratio, right? So the English language is very irregular, right? For example, the letter E we know occurs the most out of any letter. So when we're compressing something, basically we choose a number of bits to represent it. So we would take the smallest number of bits to represent the letter E. And then, we would do it sort of by statistically. And we have lots of statistics on language. The drawback, it can require more storage if it's not compressed, right? So it is sort of, well, it can take a lot of bytes to store. But I mean, a lot, this is like ancient history when a few hundred kilobytes was a lot. Not so much anymore. It can be slow to access. We get sequential access only. That's not quite true, but it's true in practice, right? It's very hard to do random access with a text file, as we'll talk about. Every field of data must be written. So a struct, if I'm writing in binary, I just take the struct, throw it in memory. But if I'm writing it to text, I have to decompose all of the values, right? So I have to say, well, the student name is this, I'll write that. The student grades were this, so I'll write those. So on the other hand, binary is very fast to access because it's kind of more regular. I know if I want a piece of the data, I know where to go to get it. It can require less storage, uncompressed, but it has a low compression ratio because it's, again, while the English language, we have a lot of data on statistics, which words are most common. When you just write binary data, there's no real statistics, so it's harder to compress. You could be writing anything, really. Advantage, we can read and write whole structs, though. We don't have to take everything apart. We just say, well, throw those 20 bytes to disk, and I'll just load them back into the same struct, and it'll be fine. If something goes wrong, you're out of luck, right? It's just really hard to put back together. If Humpty Dumpty breaks, it does not go back together again in binary, whereas when you corrupt a text file, you can sometimes fix it. So our streams will end with a special end of file marker, similar to this null bit at the end of a string. In C, it is predefined as a constant EOF. In our system, it has a value of -1, although that's not necessarily the case in different systems. And so some of our C library will return this end of file mark. So we're going to use this constant. Something we're not going to do is read and write to devices, but if you wanted to, C has some functions to do that, but they are, not as independent as files. So they would look something like this. I can open a path, right? Because at the end of the day, if I want to say send some bytes to a printer or whatever, I can open technically a file, which means I just open I just reserve a bus, right? A bus is a collection of wires that each one carries 1 bit. And then I just send some information over that bus, which is like I'm writing to a file. And then I close it, which means I'm done, right? And then all that goes to the printer, and then the printer runs a little bit of code and prints it out. So if you want to do that, there are ways to do that. We're not going to do that, right? So these are somewhat OS dependent. So if I write that in C in Windows, it might be a little bit different than Linux. We're going to focus on files. All right, so the first thing we're going to do, our file is open it. We're going to open a file stream using this fopen. It returns a file, right? Well, a file is just an int or a long or something. It's just some sort of some size of integer. And again, the same way that we did with sockets and we did with threads. It's just an ID. I say, please send these bytes to this file. So the first parameter is the file name here. The second parameter is the mode. Read, write, and append. So what do those mean? Well, what happens when we want to read? Well, first of all, I need a file that already exists. And so this file is going to have some data, and it's going to have an end of file marker somewhere in memory on disk. And when I open a file, I'm going to get a file marker or pointer that points to the beginning of this file, right? And so then when I start reading, it's going to read this data sequentially. And when I reach the end of file, I'll get some sort of end of file marker back, and then I can exit or close the file and exit. If I open it with W, I want to write. If the file does not exist, a new one is created. If a file does exist, it's overwritten, right? So in this case, I make a new file. The end of file marker is right at the beginning, and so is my current pointer. And if I open a file that has data, well, that data is gone, right? So it's just, we just lose it, and then we overwrite it. We also have an append. So if I want to open a file that already exists and I don't want to lose the data, then this will put the file marker to the end of the file next to the end of file, and then I can start adding data to the end of it. If the file already exists, then we still get all of this new information stays on the disk, and I get to add more. In addition, I can do R+, so open a file for reading and writing. In this case, the file must exist. File marker starts at the start of the file. Open for reading and writing, but if the file does not exist, it's created, right? So that's W+, so very similar to R+, except whether or not the file exists. And then append plus opens a new file for reading and appending. The file marker begins at the end of the file, and if it does not exist, it's created. Okay, so I think we can maybe do a quick example. Yeah, so let's see here. In this code, I take in a file name and a mode as command line arguments, right? So we're going to use command line arguments here just to process all of this a little bit quicker. And then I'm going to try and open a file. And if I don't give any command line arguments, we're just going to open sample file, and we're going to open it for reading, sample file.txt. So I can do, yeah, well, we'll come back to this. So, and I cannot fopen, fprint, I just can't remember the names of them. All right, so it's going to attempt to open the file, a file name that may or may not exist with a certain mode, and then just, I did some extra stuff here that we don't need to do. And then if it doesn't open, we're going to have an error. Otherwise, it's going to open successfully, and then we're just going to close it. And we see here that we're doing a little bit of error checking on close. So this end of file marker also indicates an error when we're trying to close a file. Okay, so in this case, if something goes wrong, and generally speaking, there's not a lot that can go wrong, except that your disk drive is broken or something like that. Or, a glitch in the matrix, but yeah, so we're going to see if we get error messages, basically. Okay, so if I do T, it says I cannot open the file. So what did it try and do? It tried to open sample file.txt, which I deleted using the R mode, right? So file name, mode, sample text.r. So for reading, it could not do that. If I tried to do sample file.txt, and the mode is going to be R plus. Again, it can't open the file, right? So R and R plus, the file has to exist. If I want to do sample file.txt for writing, files open successfully, files close successfully. And if I want to append to that, that's no problem. And I want to append plus or write plus, that'll work. Okay, so no big deal, but reading and writing, I need a file to exist. Reading and the R plus, I need a file to exist. Writing or appending, it'll create it. So questions? It just means reading and writing, so I can do both. Actually, in all cases, it means that all the difference between A plus and W plus is where the current pointer goes, right? So we have when we open it, we have a pointer that points to somewhere in our file. And if it's an A, it's going to point to the end of the information that's currently there, if there's anything. And if the W, it'll be the beginning. So yeah, this will actually delete any information that's already there, right? So if I did something like, let's say hello, right? And save it, and then go back to F open. And file opened and closed successfully. Let's see. And yeah, it deleted the information that was there. All right. Other questions? All right. It gets more interesting, I promise. What scenario would you ever want to use R plus over W plus to read and write? Essentially, if if you need the file if you want to make sure the file exists, right? I want to read and write. Maybe it's a save game or something. I don't know. I mean, that's a good question. I would have to maybe think about it a little bit. But so which scenario would you want to use? Well, for some reason, I just want to make sure that the file exists before I start messing with it. And if it doesn't exist, maybe like I need more information from the user, right? So a file exists, it has the user information. I take their name and password. The file already has their address. And so if the file exists, we're fine. We can just append some more information. If the file doesn't exist, then maybe I want to prompt them for their address, right? Something like that. Yeah. All right. Other questions? Yeah.
And would you do like write like something like 8 plus, but I would write at the end of the file? So you would be like writing and appending.
Yeah.
How would you do like appending at the end? Writing.
Just let's just see if we can modify it a little bit to do that. Did I call it open? Let's just write a little text. We will go over some of the ins and outs of doing this. So my file is open. I'm going to just add some stuff to it. Fprint F. So the file descriptor and oops. Hello. Okay, so this is a very simple way to add stuff to a file. So I'm going to say sample file.x. I'm going to say hi there or .text. I'm going to save it. And then I'm going to run this code and it should append, right? So if I say and didn't do anything, right? Open. Just print this. All right, something went wrong, but yeah, that's the idea anyway. So if I had somehow, whatever mistake I made, I'm not sure, but if I had somehow done that correctly, then I would get like a hello that would appear here, which that's sort of strange. T sample file text. Oh, I didn't, you know what? I didn't compile it. The most basic of all of the, so yeah, here now, yeah, you can see a hello got appended here. All right, so other questions? Okay. So that's basic opening and a little bit of writing. So yeah, it's also good form. Every time we open a file, we should check to see that this operation completed properly, right? So if this returns 0, then I have a problem, right? So if it's 0 or null, then maybe I want to print an error and exit. Especially if it's for writing. That means, you know, even if the file doesn't exist, it should have opened, so something else went wrong. At that point, I'm probably done with files in this program. We can even compress that a little bit. So I can declare my file descriptor, and then I can assign it the outcome of this and also check to see, right? So this is fancy programming. But technically, this assignment operator, right? It also returns this, after it assigns 1 to this variable, it returns the variable. And then I can use that variable in the next expression and compare it to null. All right. And yeah, so the situation that we were talking about, the only real difference, or maybe like the one thing you should know about the R is that the file has to exist. And if it doesn't exist, you know, we can maybe ask the user if they want to create it, and then we can ask them for their address or whatever other information we need before we open the file. And then the last thing we should do is close the file, right? So then we just take the file descriptor, call close, it returns some error code, right? Same as sockets, same as threads. Well, not really same as threads, but same as sockets. All right. Questions? Okay. Some other functions that you may or may not get some mileage out of. So I can check, I have this file descriptor. If something happens, I can check to see if there's an error, right? If I try and open it and it doesn't open though, I technically don't get a file descriptor, right? So that open returns null. And if I try to check to see if there's a error in my null pointer, I'm going to get a seg fault, right? So this means that the file is open and something went wrong along the way. Tried to read bad date or something. If there's an error flag, I can clear that error flag because error flags can sometimes mess things up, right? Maybe I tried to read something, it didn't work. I clear that and I try and read it again. I can check to see if the end of file has been reached on this particular file descriptor. Okay. All right, so let's read and write. You just saw how to do it with a print, but we're going to start with binary encodings. And right, so if I just want to write straight binary, I'm going to have a pointer to some sort of data. It's going to hold the thing, and then I'm going to say that data has this particular size in bytes. Of n of these things, right? So there's a little bit of flexibility here in terms of we can actually, if we know the exact size of the thing we're writing, you know, it's just a little bit of math to change these numbers around and get the same output. And then the last thing is the file descriptor. All right, so then let's see an example of this. So yeah, here, well, let's jump into, what is it, F write. I mean, I don't know. I can't. F-write example. They all start to look the same. So here we have a struct. This person struct has a name of 10 bytes, has an age, which is an int, and a weight, which is a float. Right. So there's a note here. The fixed size is much easier to read and write to a file. Variable size, we're going to see some of the problems inherent in that. So in my main, I'm going to open a file, and then I'm going to write out some data. Right. So if I want to write this float, I'm going to do fwrite. What is it? And we need the too few arguments. No, sorry. Oh yeah. I need sorry. Size of. So I'm confusing this with another function call. So this is my data, and then I want the size of the data that I'm writing. Well, in this case, it's the size of a float. And then the number of these things I'm writing is 1. And then the last thing is the file descriptor. And then this should, right, I've opened the file. Down here, I'm going to close the file. And this should write a float to that first location. Right, should. Questions? Okay. Let's try and write a sentence. This is a sentence. Let's get rid of this. I want to write out this is a string, a character array of size 30, right? This is a sentence, has less than 30 characters, but, right, so like being flexible about the amount of characters is probably a good thing. Or sorry, not a good thing. We want to have an exact size. So, oops. Sentence, right? So any array is just a pointer. So this fwrite takes a pointer. So I can just use that array. Size of, well, it's an array of characters, and there are 30 of them. And this is the file descriptor. Okay. Let's write it and see what we get. So we opened up this sample file.dat. This is binary. All right. Okay. So it opened, it wrote a float, and this is a sentence, and then it closed into the sample file.dat. And now I'm going to say, oh, I just want to look at it anyway. And you can see that the characters actually are recognizable. So it's going to take this file, which is just a sequence of bytes. It's going to basically read the ASCII table, right? It's going to convert it into an ASCII file, a text file. So some of that's recognizable, but some of it isn't, right? So this up here is presumably my float. There's maybe some Unicode there, I'm not sure. Then my sentence appears, and then, well, a bunch of nulls, right? So there's a bunch of zeros. So that array of 30 characters, everything after this is a sentence with 0. And that's what got written out here. So some of this stuff we can recognize. All right, questions? Okay. Let's see if there's anything. Let's start reading some of that back in. So we're going to look at the different data types and some of the strengths and weaknesses, but well, actually, let's do one more thing before we do that. I said there's some flexibility in how we can do this, right? So maybe I want to also fwrite. And now the size, I want a size of sentence. Oops, size of. And then I just want one of those. And I want that written to that file. Okay, so here I said the size of a char, but I want 30 of them. Here I just said, well, the size of this sentence, which is going to be 30. and then I just want one of them. So if I run this, and then I look at sample file.dat, you can see that, well, I have the exact same thing, right? So those two things are equivalent in this case, right? So there's some flexibility in terms of, it's just basically, I'm writing, the amount of stuff I'm writing is this times this. So in this case, this is 4 times 1. In this case, this is 1 times 30. In this case, this is 30 times 1. So they all have the same effect. Questions? Okay, let's read some of it in then. So the scan example, we're going to do something very similar. So we're going to read back the float. So we want f read. We're going to read it into this float, and it takes a pointer. All right, so we want the address of, and then it's basically the same thing. Well, how much am I going to read in? The size of my float, and there's one of them, and that is my file descriptor. And I actually want this above where I print it, right? So I'm going to read in the float. I'm going to print off the float, and then we'll just sorry, I don't think I want that. That may get us an error. But yeah, there's a bunch of other stuff we're going to do. But the first thing we're going to do is read in that float, hopefully, and print it out. So GCC F. Oh yeah, so I do have some stuff printing out here, eh? So here, maybe I'll just get rid of all that. Okay, good. So we just read in a float, we print out a float. No, it's still there, huh?
I think you're on S scan example.
Oh. Oh, yeah, you're right. Good call. Like I said, I don't know, man. Something. So here I cleaned up all this. I get like so these are Mark Lante made these examples. I modify them a little bit, but he does these for whatever reason. I cannot tell one file name from another the way he writes them. I prefer like short, and so these all look the same to me. But yeah, so we're going to f read data size of float 1 FD, and then printf. The float is okay. So f read example. All right, the float is, and what did we write in? F write example. 1078.24, and what do we read out? 1078, right? The floats are horrible for precision, right? They're not super reliable. You get some, maybe you've seen weird things in Java where you take like maybe the sign of 0 and it should be 0, but it's like it returns like 0.000001 or something like that. And then you get these weird behaviors because it's not equal to 0. That's floats for you. If you want 2 bits, or sorry, 2 decimal places of precision, you should specify 2 decimal places of precision when you write it out. But yeah. Questions? Okay. So we read the float back successfully. Let's read the sentence. So F read sentence. Size of a character, 30, and file descriptor. All right, and then okay. The sentence is the sentence. So space there. Okay, so that's good. So it read in all 30 of them. Of course, when I printed the bytes, when I wrote it, it also wrote out the end of string. And so when I read it into this character array, I also read in the end of string, and it works just fine with printf, right? So it's 30 bytes, precisely the same as the other 30 bytes that were written. All right, questions? All right. Array. So again, I can do, you type fread and date again, it will read the characters as float. Yes, yeah, it will. Right, so the question is, and that's a good, yeah, let's read the next. Right, what happens if we get the thing wrong? So on the other file, oops, I'm printing here, right? I want to actually, no, this is read. Okay, so yeah, the question is, what happens if I try to read the next one as a float when I know I printed it as a sentence? And well, it tries to interpret it as a float, so I get some number, and then after it reads the first 4 bytes, it reads the rest of the sentence, right? So that is the danger in everything C, right? It's not like Python where maybe I have a JSON file and it automatically converts everything for me. In C, you have to be very aware of where I put what data, right? So yeah. If I happen to read something that is not a float, of course, I'm going to get some garbage data, but I'm also going to move the pointer ahead. So yeah. All right, questions? All right, so yeah, let's do the rest of this really quick. In fact, let's look at something that's already done and just talk about it. Yeah, right. So here I write a float, here I write a sentence, an int array. So I'm going to write this in 2 different ways, basically. So I have 5 of these integers. I can write them. Actually, again, I do want to focus a little bit on this int array. So I'm going to write the whole array at once, right? So the size of int array, that's going to return 20. And I'm going to do that once. And then these numbers are going to be written. Right example. And then if read example, which will be, well, actually, let's take a look at the, okay, so this is a sentence, and then I got the rest of these 30 characters, and then this is apparently the array. And then down here, I wrote some other stuff, which I guess didn't get, but let's focus on the array of integers. Right, so I got null, null, null. So I can see the 4 bytes. I got 0, 0, 0. And here I have a quotation mark. And if I look up ASCII table, so what was the number? The number was 12 or 34. So it's not 12, but 34 is the, you can see here, well, you can see that it's the quotation mark, right? So it converted that integer, that 34, into ASCII code, basically. Same thing in 1406. Oh, is that right? All right, well, we'll get to do it again. But yeah, you can kind of, although it is written in binary, you can kind of see, right? This is the number 8, which corresponds to, well, this is an ASCII. This is the character 8. And if I looked up the number representation, it would be like whatever the next number I wrote. All right. All right, so let's go through all of this at once then. So I'm going to, F write. So I write out the array, and then I'm going to write out, well, maybe I only want to write out part of the array in this case. So I'm going to write out 3 of them. So this array, the same pointer, the size of now is the size of the data, which is an int. And I'm going to write 3 of them. So this should write 12, 34, 56. My struct. So I had a person struct that had a name that was like an array of 10 characters, and then a age and a weight. So I can initialize my, right, using the curly braces, I can initialize my structs with values. So these just write this into memory. And then, well, it's an array. And so I can write it out a couple of different ways. I can write it out, again, this is a pointer. The size of my friend's array, so this is going to be 4 times the size of the struct, whatever that happens to be. So it's like 10, 4, and 4, so 18 plus whatever padding is there. Yeah, I don't know. So it'll be the size of that struct, and I'm going to write it out once. Or I can write out a single part of that struct. So in this case, I want the size of a struct person and 1. Or let's say I wanted to write the Marie out instead of Bob. I would say 3. But now this is no longer a pointer, right? When I use the subscript, this now returns a struct. So now I have to take the address of this thing. All right. So then this should write, a bunch of stuff. So it's going to write my float, my sentence, my array, the first 3 characters of the array, and then an array of structs, and then it's going to repeat the last person. Right. Oh yeah, sorry. Let me update this. No, that should be fine. Okay, so I'm going to write sample file.data. Well, there's no new lines in there, so it's all on one line. But you can see I wrote Marie here, and Marie appears twice, so that kind of indicates that something went right. And then I this file, and again, it's important that I read it in the exact order that I wrote it, right? So I got the float, again, trouble with the precision. I got the sentence, I got the array of 5 integers, and then I can read the first 3 elements of the array, and I can read all of the structs. And I guess we didn't go over that piece of code, but if we look at it, yeah, so it says here is the array. I read in the entire array at once, right? So I allocated some space. I wrote the array into this, and then I printed it out. I decided to read in the first 3 characters. Actually, let's do something else. Int, just to show that it works. if I wanted to read in the next three characters into this. Right, so that should do that. The structs, so I declare an array of size 4 of person structs. I read them all at once, and then I get, right? So it's just 20 bytes that read into that file, and then I read 20 bytes out in the exact same order, and I get the exact same structs back. And then the last thing I wrote was an individual struct, and so I read that one. Of course, in this case, friends is a array, so that's a pointer. Friend is a struct, so I need the address. And then I can print out that person. And so, yeah, even using the different array, I get back these three characters. All right, so that's, reading and writing in binary. Questions? Okay. And yeah. So that brings us to text input output. And in some ways, this is simpler, and in some ways, this is a lot harder. So we're going to use fprintf, which we've already seen, and fscanf, which these are similar to printf and scanf. And do a string print and a string scan, right? So we can read and write to and from an array of characters. So in this case now, if I want to write a float, I would do it like that. So I start with the file descriptor, and then it's basically a printf, right? So I do the string, I do the whatever the type marker is, and then I put the data. And the same for the scanf. All right, so we will get to that, but there's a few things to consider when we are using text files instead of binary files, right? So binary files, they work fine. We can pack the data like right next to each other, right? I can put a float next to a float because when I read it, I read a float and that gives me 4 bytes, and then I read the next float, that gives me 4 bytes. I don't need anything in between them to tell me that this is the end of the float, right? I just know this because I know a float is 4 bytes. But when I'm using text now, well, the end of the float, where does it happen? It could be any number of bytes, right? So when we're reading and writing binary data, we have fixed sizes, which is nice. We can organize things. We can say this goes here, that goes there. As long as we remember, we're fine. If we mess up, it's a disaster. We basically have corrupt data now. But with text, that's not necessarily true. Everything sort of takes up a different amount of space, right? So how much space does an int take? Well, if I write out I, that's going to take 1 byte. If I write out j, that's going to take 2 bytes. If I write out k, that's going to take 3 bytes, right? So, and yeah. And so you have to consider stuff like this. So I want to write 3 digits. Okay. So I'm going to write 3 digits, and I'm going to write them to, now it's a text file, so sample file.txt. So I'm going to use the fprintf, so the file descriptor, and then, oh, what am I going to get out of this? Am I in the right place? Yeah. Fatal error. Okay. So then if I look at sample file.txt, this is my 3 numbers now. Okay. So that's not good, right? If I go to yeah, here. If I go to fscanf and I try to read that data, I'm going to have some problems. Right, so again, fscanf, sample file.txt, but now I'm opening it for reading. It already exists. I make 3 ints and I try to scan them in the same way that I scan them out. And Here's the data. So that's not the numbers I put in there, right? So it reads the first number and then it reads, I don't know, maybe there's some, there's probably, is there an end of string there? Not an end of string, but maybe there's some sort of garbage there. Anyway, it's not what I put in. So we have to be very, very careful of making sure that the text is, if I'm writing 3 numbers, I should at the very least, maybe put a space. Maybe something different, but at least a space. Okay, so I write the numbers into sample file.txt. Now they're separated. And now if I ran I get back the data, right? Exactly as I put it in, even though on this side, I didn't put any spaces here, right? So writing it in or reading it in is a little bit, again, I don't know, you got to be careful with this stuff. It's a real nightmare, I swear to God. Figuring out all like how to, for instance, if I'm going to take my data and write it to a text file, figuring out a format that will work in all cases, good luck, right? This is the idea behind a lot of exploits, is that they can exploit the way your data is stored, right? So if it's a comma separated, what do they call that? CSV. So if your data is comma separated and then I put my name in and I put a comma in there, like that can mess up your entire file, right? And that was the idea behind like SQL injections for a long time. I think they're no longer a thing, but they used to be a big deal, right? You could actually literally go to a website and kind of hack in by using SQL codes, right? You just you put a closed, what do you call it, quotation mark, and then that represents the end of the string. And now I can write actual SQL code, like, grab all your information and write the file and then try and pick up the file later, something like that. So yeah, you have to be careful of this stuff. Questions? Okay. Let's look at, so here I print this. Okay, so let's write a sentence now. So I printed out my 3 integers plus a new line because I want things to look nice. And then I'm going to print out a sentence. I'm getting tired of compiling this stuff, so right, you guys remember make files. So let's do print and scan and print. Depends on, what is it, fprint.c, and then gcc-o print.c, right? So if I change print.c and I hit make, it's going to call this print command, and then it's going to execute this. And then I want to do the same thing for scan. And F. Oh. So I picked up a lot of stuff there. All right, so now I have, what the hell did I do? fscan f. Okay, I think that's good. So now I have a make file, so I can just make both of these things at once. Fatal error, no such file or directory. Print f. Okay. So now I can write print, and then I can do scan. All right. Okay, so I wrote out this is a sentence, but I didn't read it in. You can see that I did indeed write out the 3 numbers, and then this is a sentence. Let's scan that in here. So I guess it's already set up. So we're going to make an array of 30 characters. And we're just going to read it in the old-fashioned way, right? So this, well, yeah, spoiler alert. What happens when I scan in a string is that this scanf stops at all delimiters that are white space. So yeah, let's do make. All right, so the data, it read incorrectly. The sentence, it only read as this. And so yeah, well, there's a couple problems here. So on the other end, it printed out everything fine. But how many characters did it print? Right? Like it didn't print 30. When I did binary, it was easy. I just take this whole thing, I say 30 bytes. It's going to include a bunch of stuff that is empty, but that's fine. I don't care. I read in 30 bytes, and as long as the sentence, the sentence has to fit in that 30 bytes, right? Because I'm reading from a character array of 30. But now in this case, I have a variable size sentence. I don't know how big this sentence is. And if there's any spaces, well, this is going to give me a problem. So if we can agree that I want to send 30 bytes, well, I can try and read 30 bytes. But I didn't write 30 bytes necessarily, right? I only wrote the size of the sentence. So if I did something like I can read in 30 characters. Actually, let's try that. Oh, sorry. This side works. Actually, fscanf, if I read in 30 characters, then yeah, it reads the entire sentence. Also getting some weird effects here. I'm reading in that last new line, right? So you have to be careful with this stuff because what am I reading there? Why is there a new line? Well, I'm actually reading, if I go back to the file, I'm reading the new line that was printed after the numbers. And then I'm reading this sentence, and then I'm reading that new line and whatever other garbage I can find in this file, right? And if I put data after this, well, it's going to read that too, right? So that's going to cause problems. So it is really important that the number of bytes that I write is the same as the number of bytes that I read. In particular, if I'm going to store more data after this, right? Then it has to be exact. I can't, if I'm off, I'm going to ruin all the data. All right, questions so far? Okay, so what are our options? Well, we have a few options. One of them is that, well, I can just print out 30 characters. Actually, I can just do this. Anybody remember what that's going to do? For sure, 30 characters it's going to print out, but what's that going to look like? Sample file.txt. It's 30 characters, but it's right justified. All right, so that's not the greatest. If I wanted left justified, I'm going to put the minus. Wish these were closer. Sample file.txt. All right, this looks good. There's a new line, and then there's a bunch of spaces, and altogether there's 30 characters. So that's fine. That's actually not a bad thing. When I read it in now, I'm going to read in all 30 characters, and then that should again, I'm picking up that last new line, so I should fix that. And then it reads in the sentence, another new line, and then the rest of the spaces to cap that out. That's not great, right? But it's better than just getting the first letter. And also, I'm not corrupting all the data around it, and I can maybe go through and fix this after. All right, questions? Okay, so a couple of other solutions for this are, well, I could just write out how long the sentence is, right? On the print side, I can say this is a sentence, and let's keep, we can keep the new line for now. And I'm just going to print it out, right? But before I do that, I'm going to print out how long it is. So I'm going to do something like this. I'm going to say fprint fd. We might complain about this data type. I'm going to put a space, right? So I'm printing out a number, and now string length of sentence. Oh, well. Should declare it before I use it. Okay, so now I'm going to print out the length of the sentence, and then I'm going to print out the sentence itself. Yeah. Implicit declaration. Did I get that wrong? Oh, fprint f. Okay. Yeah, it doesn't like that. It prefers long. All right. So just in case my sentence is more than however many thousand characters, I can print. That will do. This is a sentence with a 20 in front of it. So then I just need to read that in on the other side. So I guess let's steal this. I think if I leave a space there, that might help. And then I'm going to, well, now I have to scan in one character at a time. So I'm going to loop sort of everything in C has to be kind of a little bit of a pain. Otherwise, it's not proper C code. And then we will scan character by character. Like this. Okay. All right, so I'm going to read in the number. I think this will get rid of that space, maybe not. We might have to adjust for that. And then I'm going to scan in just one by one, all of those characters, and then print them out. Oh yeah. This is, I believe that needs a pointer. All right. All right. Pretty close. Right. So I did get the, well, what did I read in the last thing that I read in? That is the I guess that, well, I read in the new line, this must be the string delimiter. Or I picked up a piece of garbage somewhere. Anyway, hopefully you get the idea, right? So when I'm reading and writing strings, now I have a bunch of problems with formatting, especially sentences, right? So obviously something's not quite perfect here. I'm picking up an extra character at the end, but hopefully you get the idea. So questions, 10 minutes left. All right, one last, this is like to heck with fscanf and fprintf. If I have a character array, I just want to write it as bytes. Right, so maybe like forget all of this. I'm just going to write my sentence as F right, sentence, size of the sentence, write it once, and then that's it. I don't have to worry about and then on my scanf side, I will do F read. And then just print it out. Right, so I can mix and match bytes with character data. And then if I write scan, here's the data, here's the sentence. Again, I'm picking up that last new line there. That's hanging on the buffer. I swear to God, buffers are like they'll be the death of me. But yeah, I can do that. I can mix and match. And then if I look at sample file, this is a sentence plus a new line plus a bunch of null characters. So yeah, questions? All right, there's dangers of doing that as well, of course, right? So yeah, this describes all the problems that we just went over, except for the last one, right? I can do things like, well, actually, I think I have an example. So cards.c. So let's say I did exactly that. I opened a file cards.txt. I'm going to write a digit 76, and then I'm going to write another sentence, 52 cards in the deck. I'm going to close the file, and then I'm going to reopen it for reading all in the same place. So then I'm going to do the exact same thing. I'm going to read in a text digit. I'm going to print that out, and then I'm going to read in the sentence as a byte array. So do all of that. So of course, what gets printed out is not 76 and then 52 cards in the deck, but here I have, these two numbers combined. Right. So even when I'm writing out a character array as bytes, if I read it as ASCII, I can still read it back as text. So there is a danger of like these two things getting fused. Yeah, so 76, 52 cards in a deck, plus whatever all this was. All right, questions? Yeah, so when you're reading and writing binary files, of course, as long as you know where the data goes, you're going to be fine. It has some other advantages, which we're going to see. If we want to do text, there are advantages in that, like now I can read a configuration file. I can also read it into my program and make use of it. But I got real problems in terms of like separating my data. So do I want to separate it by spaces? Do I want to separate it by commas, tabs? I have to be very careful. Do I want to just sure that I write a certain number of characters? And again, bad actors can exploit the formats that you use. And but if you're writing in binary, as long as you remember where you put everything, you're going to be fine. If you mix, there's other problems as well. Yeah. All right, yeah. So this is the example we just saw. Okay, 5 minutes. We'll start talking about file positioning. So one of the weaknesses of text-based files is that I can only access them sequentially. Like that's not true. I can actually jump anywhere I want. But the problem is I don't know where to jump to, right? So here I have an int array of size 5 with these numbers. If I write them to a text file, I have something that looks like this. And so now I ask you, give me back the fourth number. right? So just jump in the file to that fourth number and read it back. Well, it's a text file. You don't know how many bytes it is to get there. So you really have to read in, everything that comes before it and then say, oh, now I got to the fourth one. Now I can give that back to you. That is not the case when you read and write in binary, right? So yeah, text-based encoding tends to have variable sizes. Even when we have like uniform data types, the values are going to take a different number. But, right, when I read and write binary into memory, read and write to and from memory, well, it's kind of easy, right? If I want the fourth thing, or like in this case, yeah, the fourth thing, index number 3, I could just do pointer arithmetic. I could just say, well, you have a pointer to the beginning, jump 3 of these ints, right? So that means I jump like 12 bytes. And then I just grab whatever's there, and that's going to display 88 in this case. Okay, so when I read and write from memory, I can do random access, right? I could just jump to where I want, and that applies also to files, right? So when I read and write to a binary file, I have a file marker. Why do we use star instead of ampersand? Oh, here. Yeah. Right. So scanf takes a pointer. So if this was scanf, then I wouldn't have these. But printf needs I need a value, right? Printf does not print a pointer. Well, if I can print a pointer, but reference. This is right. All arrays are pointers, and all pointers are technically arrays. So yeah, I have to dereference it. This tells it that I want this value, and then 23 gets printed out here, and the same for over here. If it was scanf, then I need, right? Well, then I can just use pointer arithmetic, or I know it's so difficult to remember in the beginning. But if I do this, this is technically like I did a star. And so now this gives me back the fourth element. And if I'm doing a scanf, I would have to, if I wanted to read into the fourth location, I would have to use a pointer. I don't know. My only answer is like practice. It's just difficult. It's a lot. Is the given add order function main.c. When you add it, no, I think isn't that code you guys have to do, right? Add order, I mean, you have to have a functioning queue for that to work. So I'm pretty sure I gave you correct code, but if I didn't, please let me know. Yeah. Oh, makes an order and then adds it to the queue, right? It works for me. If you're doing, if you're implementing queue differently, feel free to change it. Like if it's not working for you, if you want to do something else, go ahead. But yeah, other questions? All right, we'll end there. That a lot of jumping around into files in that one. So next class, we will probably finish talking about files. We'll look at this random access and how we use it, and then we'll look at pipes and stuff like that. Oh, actually, no, next class is midterm review, right? So we'll probably do some lecture, but mostly midterm review. Yeah.
Do you have the sample for assignment 3? Because I wasn't able of doing it, and so I like know pretty much nothing about structs.
Like the starter code,
No, like the whole assignment.
like the solution.